So welcome to the introductory colloquium series on the ECT STAR scientific workshop program. The intention of this colloquia is to introduce the topics of the workshops and publicize them to a wider audience. And today's colloquium will be given by Marco Dreves and concerns the workshop entitled New Physics Searches in Heavy Ion Collisions, which will run as an online workshop in May 2021. For the precise dates, please consult the ECT STAR website. So let me introduce today's speaker. Marco Dreves obtained his PhD in 2009 from the University of Hamburg in Germany, and currently he's a faculty member at UC Louvain in Louvain-la-Neuve in Belgium. And in his work, he's interested in early universe physics and physics beyond the standard model, for instance, in the context of neutrinos. His colloquium will introduce the workshop, as I said, New Physics Searches in Heavy Ion Collisions. And the main ideas are to explore new physics searches which are absent or suppressed in standard proton-proton collisions, and also to take advantage of the different backgrounds that occur in heavy ion collisions. And the workshop will bring together scientists from different fields, so experimental physics, theoretical physics, accelerator physics, and detector physics, to be able to address these questions thoroughly. Okay, over to you.
All right, thank you very much. I would have very much preferred to come to Plento in person. But since things are the way they are here, I hope we can make the best out of it with this remote format. So today I'm going to talk about new physics searches in heavy ion collisions, which is a relatively new topic and, still relies on innovative contributions from the community. And I hope I can get you excited about this idea. So let's start with the general picture. So the Large Hadron Collider was built for three different purposes. So first, it should unveil the origin of electric symmetry breaking. Second, it was expected to find new elementary particles, like supersymmetric particles or others that relate to open problems in particle physics and cosmology, such as the dark matter and so on. And finally, it's meant to study the quark-gluon plasma, the properties of the quark-gluon plasma in heavy ion collisions. Now, if we look back at several years of LHC running, two of these three goals have been achieved. A scalar particle has been discovered, which very closely resembles the standard model Higgs boson. So most people are now convinced that the Higgs boson was discovered, and there was already a Nobel Prize for this. And also the knowledge about the quark-gluon plasma has greatly increased. What has not been found are new elementary particles. This is somewhat disappointing. However, we know that they must be there because there are several problems in particle physics that definitely require the presence of new particles. For example, the neutrino masses, the dark matter, the matter-antimatter asymmetry in the universe. And there are also some theoretical arguments that suggest that the existence of new particles with masses that are not too large, like the electric hierarchy problem. Okay, so what do we do? Well, one way to proceed is to build a bigger collider, the FCC at CERN or the CEPC in China. And this is, of course, I think this is very important to push these kind of projects because one can explore new energy scales. However, the time scale in which these projects will be realized is rather long. So it will be, for the FCC, it will be the middle of the current century that this machine might start taking data if it is built. So what can we do in between? Well, I think, and many other people share this opinion, I think that the best thing to do is to make optimal use of the existing facilities. So to say, let's use the accelerator facilities that we have and try to turn every stone. Maybe in the first searches at LHC, we were too focused on looking for supersymmetry, we were too focused on looking for certain signatures. Maybe something slipped through our hands. And there are many approaches that go into this direction, for example, searches for displaced signatures and so on that now have started. And the search in heavy ion collisions is part of this, this broader program to fully exploit the discovery potential of the existing facilities. The key question here is, where is the new physics hiding? And schematically, one can look at this, well, where's the new physics hiding and why haven't we discovered the new particles yet? So schematically, one can visualize that in this picture here, which is the two-dimensional representation, where in one direction we see the mass of the new particle, on the other axis we see the coupling that it has to particles that we know. And here we see, like this symbolic map, the standard model represented by a castle that is sort of resisted every attempt to breach it. So it still holds in almost all measurements that that we've seen in experiments are consistent with the standard model. And then the new physics could be searched for in two directions. Either it has not been found so far because the new particles are too heavy, or in this case, we simply couldn't make them at the LHC because the center of mass energy is not large enough. Or the other possibility is that these particles are very small couplings with ordinary matter. In that case, the branching ratio is the problem. So in principle, we could make them, but they're being made in very small amounts, and one has to look very carefully to find them. These two approaches the experimental programs to explore these two possibilities are called the energy frontier and the intensity frontier, one increasing the energy and the other one decreasing the number of events. So currently LHC is clearly the front runner at the energy frontier, while on the intensity frontier there are several existing experiments. I named two here for the case. It's like T2K or T2K in Japan or NA62 at CERN, but there are also others. In the future, this will become more. So at the energy frontier, we expect the future colliders. At the intensity frontier, many different proposals have been made to build other experiments. I just name a few here: Methuselah, SHIP, Codex B. There's also Anubis, Alex. So both of these frontiers are being pushed in the future. The question is there something that we can do with heavy ions? Maybe something that can be done before these future facilities are being built. All right. So what gave rise to this idea, or something that gives hope here, is that many things are possible in heavy ion collisions that were not thought to be possible many years ago. So for example, top quarks have been found in both proton-lead collisions and also in lead-lead collisions. And then these top quarks can even be used to study the properties of the quark-gluon plasma. So I don't think in the original motivation to do heavy ion collisions at the LHC was not to study top quarks, but it turns out that it can be done. So this brings up the question, maybe also other things can be done that were not initially in the motivation for the heavy ion collisions at the LHC. And there has been already a first workshop, a dedicated workshop topic in 2018 that we organized in Louvain. So if you are interested, this is the website where you can find it, and all the talks were recorded, and some are better, some are worse quality, but all the material is there. So if you're interested, you can look it up there. And there was also a paper that has been published as a result of this paper down here, in which most of these ideas that have been presented at the workshop have been summarized, and some references are given. So I invite anybody who's interested in this topic to maybe start reading with this paper and then follow the references therein. But let me give you a short overview of the different possibilities that have been explored so far. So heavy ion collisions can be useful for new physics searches in two different ways. On one hand, they offer new production mechanisms that are not present in proton-proton collisions. On the other hand, the difference in heavy ion collisions are different. The backgrounds in heavy ion collisions are different from those in proton collisions. So talking about new production mechanisms, one can then again distinguish production mechanisms in the strong electromagnetic field generated by the ions and production in the collision of the ions themselves. And as far as the backgrounds are concerned, I will talk about the advantage that the absence of pileup offers, and then how this can be used to modify, to change the triggers as compared to standard searches at LHC. All right, let's start with the new production mechanism, and let's start with production in the strong electromagnetic fields generated in so-called ultra-peripheral collisions. So what that means is just in flyby collisions. So this is illustrated in this picture here. So if you have these bunches in the LHC crossing each other, not always two ions hit each other, but they might just fly by each other at a short distance. And because both of these are highly charged, so these have strong Coulomb fields around them, when they pass by each other, this generates a very strong electromagnetic fields. So what defines flyby is that the impact parameter b, so the distance between these lines, these trajectories, is much larger than the radius. And the advantage of that is that basically if the nuclei don't really hit each other, then there are no hadronic backgrounds. So there's no hadronic physics. And how much of an advantage that is, you can see by looking into these two pictures, here. So this is one of these flyby collisions. Looks like a very clean environment in the detector. And this is a head-on collision where the nuclei actually hit each other. And here you see there's a lot of hadronic physics, like there are many, many tracks in the detector coming out. So there are a lot stronger backgrounds. All right, so in fact, these electromagnetic fields generated in heavy high collisions are the strongest ever created in the laboratory. They're really, really big. And this can be used to do light-by-light scattering. And this has been done at both CMS and ATLAS. To understand this physically, one can use the so-called equivalent photon approximation. So, of course, in principle, we are having two classical fields. Well, the Coulomb fields of the nuclei are sort of classical electromagnetic fields, and they do not correspond to what is called number eigenstates in quantum field theory. They don't correspond to a definite number of photons. However, in this regime, in these ultra-relativistic collisions, we can in good approximation, picture the electromagnetic field of these ions that meet as a bunch of near on-shell photons that meet each other. This is the so-called equivalent photon approximation. So here, here in this photo, the important point is that in this equivalent photon approximation, this photon number is proportional to z squared, which is where z is the charge of the nucleus. That this overall z squared enhancement is the most important factor in this formula. And then if you calculate the production cross-section for new particles that can be produced in light-by-light scattering, you can consider these kind of diagrams here. And using this equivalent photon approximation, one can calculate what is the production cross-section for new particles. And the key point is that in light-by-light scattering, because you see that the photon number goes as z squared, because it's light-by-light scattering, the rate goes as the fourth power of z. So there's an enhancement to the fourth power of z, the charge of the nucleus. And if you think about a lead nucleus, that's about a factor 10 to the 7. So this is a gigantic enhancement factor. What of course one has to keep in mind is that the integrated luminosity of heavy ion runs is considerably lower than that of proton runs. So in general, you would think that the luminosity the integrated luminosity is much lower in the heavy ion runs. However, this enhancement factor 10 to the 7 implies that the heavy ion runs are nevertheless competitive to the proton runs. And here we can see the effective luminosity of these gamma-gamma scatterings as a function of the center of mass. And here what the black curve shows you is the case of proton-proton collisions. And what the red curve shows you is the heavy ion collision. And then you see for large masses, the proton runs are definitely better. But for masses below around 100 GeV or a few tens of GeV, the heavy ion runs give the bigger effective gamma-gamma luminosity, the better light scattering luminosity. Now this only is like, okay, it's half an order of magnitude, fair enough. It doesn't look, it's an improvement, but not a gigantic improvement. However, what one has to keep in mind is that in proton collisions, the pile-up makes it necessary to tag the protons with dedicated, to tag the particles with dedicated detectors. Now, this is not possible for a small, if the invariant mass is too small. So this is why the real integrated luminosity goes like this curve here. So it basically is cut off somewhere at a few tenths of GeV because of this lack of possibility to do the tagging. And because of this, you can see that the effect integrate. So in lead collisions don't have this problem because there's no pile up, and therefore this tagging procedure is not necessary. And therefore you can see that the effective gamma-gamma luminosity, in fact, is several orders of magnitude larger than in proton. Also, this is what is said in this plot. Now, this has been turned into an estimated sensitivity estimate for the discovery of axion-like particles in these heavy ion collisions. And here you see in the x-axis, you see the mass of the axion-like particle, and here you see its coupling. And here you see there are some existing constraints in this plot, and here you see what can be done with CMS. with current data and with a future projection. Okay. So another thing that can be studied in heavy ion collision is the G-2, in particular the G-2 factor in the third generation. So this dipole moment can be described at a theoretical level by some effective operator like this here. And this kind of effective operator, apart from giving rise to this G-2 factor of leptons, it also gives rise to processes like this in heavy ion collisions. And okay, now you can say if I have some new physics that contributes to the G-2, one can parameterize this. Then this effective operator would not just have the standard model contribution, but there would be some contribution from this new physics. One can parameterize that in the way shown here. And then one can study constraints on these deviations from the standard model predictions that can be imposed by observing heavy ion data. And here in this plot here, you can see that the heavy ion data, so this green curves here, they give very, very strong constraint compared to other existing, they can give very strong constraint compared to other existing experimental constraints here in blue. Yet another thing that can be studied, which is new physics again, is magnetic monopoles. So qualitatively, one can distinguish two types of magnetic monopoles that are being discussed in the literature. The first one would be an elementary magnetic monopole, which is known as the Dirac monopole. The second type is a extended, well, let's say topological field configuration, the so-called Polyakov monopole. While this Dirac monopole in principle is a point-like thingy, due to screening effects, effectively both of them behave like extended objects. So they are not really to be thought of as elementary particle, but rather as object with a certain extension. And this makes it very difficult to produce them in proton-proton collision, because it's very difficult to produce an extended, sort of spatially extended field configuration in a point-like collision. And because of this, it's extremely difficult to make these magnetic monopoles in proton-proton collisions. However, it has been pointed out that the Schwinger effect in the strong electromagnetic field in heavy ion collisions permits a non-perturbative production of these particles. This is what is shown here. So if you create sort of magnetic monopoles from empty space through these B fields. So this is the B field equivalent of the Schwinger effect. And one can see here in this plot taken from this paper down here, one can see that the heavy ion collisions impose some of the strongest bounds on the existence of these magnetic monopoles, where the other bounds are coming from studying neutron stars or from cosmology. The blue stuff is cosmology, the red stuff is from neutron stars, and the green stuff is what you can impose from heavy ion collisions on what you will be able to impose from heavy ion collisions using the full LHC data. This is very interesting, and there is also even a dedicated experiment looking for this model, and for monopoles, which is called Moodle. All right, so much about the production in flybys. So this was all so far things that can be done in gamma-gamma scattering, so in light-by-light scattering. So now let's look at the heavy ion collisions themselves. So the case where the two nuclei actually are smashed into each other. So this is what heavy ion collisions are actually done for, and the goal is, of course, to generate a quark-gluon plasma. So how can this benefit? Well, one way how this could potentially benefit is that in such a plasma, the properties of particles are screened. So they're screened due to so-called thermal masses, so they're in effective in-medium dispersion relation, and this gives thermal masses to the particles. In particular, it gives thermal masses also to the gauge bosons, which are in principle otherwise massless in vacuum. So the photon obtains a small mass, and also the gluon obtains a thermal mass. And this can open up, this can kinematically open up production processes that would be impossible in vacuum. It has been hypothesized that this can also, a similar mechanism can play a role for the dark matter production in the early universe, because also in the early universe, one has a hot thermal plasma, just as in a heavy ion collision. Now, if one does a simple back of the envelope calculation, the the most basic idea to thermally produce dark matter in heavy ion collisions doesn't really work, simply because the lifetime of the quark-gluon plasma is much shorter than the period for which the quark-gluon plasma filled the early universe. So we are comparing here some split second to, so in the quark-gluon plasma in a heavy ion collision only exists for a very small fraction of a second, while the quark-gluon plasma in the early universe was around for, well, for 10 to the 4 seconds roughly. And this means that any particle that can be thermally produced in sizable amounts in heavy ion collisions would have produced in large amounts in the early universe, and we would probably have too much dark matter. So the very simplest implementation of this idea doesn't work. However, if you think about the fact that the conditions in the early universe are somewhat different from heavy ion collisions, there are different chemical potentials, there might have been other mediators present in the plasma. So even though the very simplest implementation of this idea doesn't work, it is still possible that this thermal production mechanism through thermal masses can open up production channels that would not be present in proton collisions that are interested in beyond the standard model physics models. Another thing that has been suggested, another possibility has been suggested, is that so-called Sexaquarks could be produced thermally in heavy ion collisions. So Sexaquarks are a hypothetical standard model state, a hypothetical color singlet state bound of 6 quarks, and they are, to the best of my knowledge, the only dark matter candidate within the standard model. So if this bound state really exists, it should be extremely stable because it is a singlet with respect to everything that we know. So it has spin 0, no net flavor, and it would have a very small coupling, and it's singlet with respect to all gauge interactions. It would have a very small coupling to other hadrons, and it would have to have a mass slightly below 2 GeV. So these are all predictions made by Glennis-Farrar in these papers here. And yeah, as I said, it should be a potential dark matter candidate. So if the Sexaquark indeed exists and has these properties, it could explain the observed baryon to dark matter density, so the observed dark matter density in the universe. And quite interestingly, it could predict these without any free parameters, because this is a standard model state, so there's no new physics, there's no free parameter. The values of the standard model parameters would predict the dark matter density correctly. However, one should say that the existence of the Sexaquark is quite hypothetical. In the community, there's no agreement about whether this state really exists and whether the prediction for its properties are correct. And since this is QCD, of course, it's a very complicated thing to prove or disprove anything. However, there have been searches already there has been a search for these things being performed at CMS, published in this thesis here. And it has been said that the thermal production, it has been estimated by Glennis-Farrar that the thermal production in heavy ion collisions would greatly improve the perspectives to observe such processes here involving Sexaquark. Okay, so let me close here for the new production mechanisms in the heavy ion collisions and turn to the second topic. So, as I said, on one hand, heavy ion collisions offer production mechanisms that are absent in proton collisions. On the other hand, even if we rely on the standard production mechanisms that are well known at the LHC and proton collisions, heavy ion collisions can still offer advantages because the backgrounds are very different. And one of the key differences is the absence of pileup. So this was already very important. We saw already one example where this is important, this ALP search, the search for axion-like particles. So recall that in principle, the difference between heavy ion and proton collisions is not so big. So heavy ion collisions are just a little bit better than proton collisions. The reason why the effective integrated gamma-gamma luminosity in proton collisions drops off here and is then so much lower than the one in heavy ion collisions, the reason for that is pileup. Because pileup makes it necessary to tag the particles. And this need for tagging is what leads to this drop-off in the effectively usable gamma-gamma luminosity here. And that's what really makes heavy ion collisions strong. So the effect of pileup can also have other advantages. For example, in the context of long-lived particle searches, it has been pointed out that the absence of pileup minimizes the risk of the primary vertex misidentification. So if you do a long-lived particle search, what you would see is that a long-lived particle is produced from some primary vertex in a collision, then this particle propagates, and then it decays at some distance from the initial collision point. But if you have pileup, of course, you have to somehow relate these final state particles and see from which of the initial vertices this long-lived particle came. And if you get it wrong, then you can't, or if you get it wrong, or if you can't identify this, if you're not sure, you can't really use this data. So because there is no pileup in heavy ion collisions, then this problem doesn't exist. Okay, maybe I should mention for the non-experts here, I've been using the word pileup all over the place. So what pileup means is that basically several collisions take place at the same time at the LHC, or so closely to each other that we can't distinguish them, and the detectors have to deal with the particles coming out of all of these collisions simultaneously, and they have to distinguish which particle came from what collision. All right, and the practical advantage that we can take of this different background that we can take advantage of with these different backgrounds is the fact that we can use modified triggers in heavy ion collisions. So again, for the non-expert, triggers at the LHC are necessary because the LHC produces a lot of data, and it's absolutely impossible. It's absolutely impossible to record all the data that comes out of the LHC collisions, because most collisions are actually not interesting. Most collisions just produce very well-known harmonic physics. So there has to be a criterion that decides when we record, or when our experimentalist friends record an event and when they don't. And for this, triggers are being used. And triggers are basically a set of criteria that are used to do exactly what I said, to decide whether an event is recorded. And these usually involve, for example, leptons with large transverse momentum. And we can already see, again, coming back to this Axion-like particle search that I already used as an example for several times, we can already see how the possibility to relax the triggers in heavy ion collisions gives us a better sensitivity. Basically, this little band here can be studied in heavy ion collisions in the low mass region. This little band in the low mass region can be studied in heavy ion collisions and could not be studied in proton collisions so easily because heavy ion collisions can use reduced triggers. And why can heavy ion collisions use reduced triggers? Well, mainly because the integrated luminosity is lower and there's no pileup. So so the amount of data that is, well, it's mainly the integrated luminosity here. So the amount of data that's produced in these collisions is much lower, and therefore one can record a larger fraction of the data, and one doesn't have to be so strict with imposing these triggers. So the looser triggers, so when I say loose triggers, I mean a sort of relaxed criteria to decide what event is recorded. They allow to explore this mass range down here. Then when I say, oh, we can relax the triggers, the question is, if we relax the triggers, we get a mess, because don't we record a whole mess of data? Because usually heavy ion collisions are considered to be a very messy environment because, well, you collide these nuclei and then you get so many tracks. And if you compare this number of tracks in the detector to what has been seen in basically any collider before the LHC and also in the LHC runs, proton runs so far, then here we have a very large so-called track multiplicity, so very, very many tracks. So one might argue that this is a way too messy environment, and if we sort of relax the triggers, then we get all these tracks, and this is not clean enough to do anything. However, the LHC people can deal with this, and the reason why they can deal with this is because of the high luminosity LHC. So the LHC will be upgraded to the high luminosity LHC, which runs at a higher luminosity. And high luminosity also means higher pileup. So in the high luminosity LHC run, we will have around 200 pileup events per bunch crossing. That gives about 5,000 charged particles per hard scattering. So for each, let's say, interesting scattering, you get 5,000 particles that you have to track. So this really changes the picture because this is then not that much less than in heavy ion collisions. So in the past, one could say that, okay, proton collisions are relatively clean, small track multiplicity, heavy ion collisions are messy, high track multiplicity. But because of the large number of pileup events in the high luminosity LHC, it is actually not true anymore that proton collisions are much cleaner than heavy ion collisions. This only makes a factor the difference is now only a factor 2 in the track multiplicity for lead collisions. And if one uses lighter nuclei, it could be that the track multiplicity in heavy ion collisions is actually lower than in proton collisions. Because of this, heavy ion collisions are actually not that much messier than proton collisions. In particular, if one talks about long-lived particles, which is something that I already mentioned just then, if one searches for new so-called long-lived particles that have that travel a significant distance, like a macroscopic distance after they've been produced and only then decay, then the signature from such long-lived particles can be rather easily distinguished from the mass that comes from the quark-gluon plasma, because if long-lived particles would be produced in a hard collision, then it travels out of the quark-gluon plasma, and because it's long-lived, it travels on and on and on, and then it decays in a displace with some displacement in the detector. And this displacement can be used to quite easily distinguish the long-lived particle signature from what comes from the quark-gluon plasma. So why am I talking about long-lived particles? Well, for two reasons. First of all, long-lived particles are one of these corner in parameter space that haven't really been exploited in the first LHC runs. So it is a type of new physics that could potentially have escaped searches in the first LHC runs. But second of all, also there are many different theoretical models that predict the existence of long-lived particles. And here I give like a little overview that I took from the Methuselah physics case paper here. Further references are also given here, where you can look up if you're interested. So there are several different motivations for the existence of long-lived particles. They could be motivated by naturalness consideration. They could play a role in the context of dark matter, mostly as mediators to dark matter. They could play a role in the context of baryogenesis to generate the matter-antimatter symmetry of the universe, or they could be involved in the generation of neutrino masses. So recall that the fact that neutrinos are massive are one of the few pieces of evidence that we have for the physics beyond the standard model, and many neutrino mass models can contain potentially long-lived particles. So the search for long-lived particles is very well motivated, and this is one thing that motivates looking into the possibility to explore corners in parameter space of long-lived particles with heavy ion collisions. So what speaks for and against long-lived particle searches in heavy ion collisions? Well, what speaks against this is traditionally people say, oh, but there's this high track multiplicity. We already talked about this, or I already talked about this. The difference between proton collisions will not be that big anymore. Then the instantaneous luminosity in heavy ion runs is relatively low compared to proton runs, for reasons that I will talk about in a sec. Then there's a slightly lower collision energy, like we are talking about roughly 5 TeV per nucleon, and for the protons it's 14 TeV, of course. And of course, when it comes to the integrated luminosity, not only the lower instantaneous luminosity plays a role, but also the fact that the heavy ion runs are scheduled are shorter than the proton runs. Most of the time, the LHC collides protons. I will exclude this last point from the discussion now because this is not a physics. This is more like a, let's say, strategic decision rather than a physics call. What speaks for heavy ion collisions? Well, each time two nuclei collide, you have an A squared enhancement because each nucleus contains A protons and neutrons. So if you collide two nuclei, well, we assume that they're of the same kind, then you get that is the same as colliding A squared protons. Second, I already discussed this fact that there's no pileups in heavy ion collisions. And third, there's this possibility to loosen the triggers at the main detectors. Let me talk a little bit about the lower instantaneous luminosity for the moment, because this is something that could potentially be improved. So what limits the instantaneous luminosity? So why are heavy ion runs performed with a lower instantaneous luminosity than the proton runs? There are basically two factors. One of them is the limitations due to the injector chains. So this means how difficult is it to actually fill the LHC rings with heavy ions? This is a technical point that I cannot comment about because it's really, we rely on the people running the injector chain. So this is an issue to be handled by the machine people, and we have to trust them that they're doing their best, which I'm sure they do. And we can't change this. The second thing that limits the luminosity in heavy ion collisions are beam losses. So the problem in heavy ion collisions is that most of the collisions are actually not hard scatterings. And if you look for physics, we look for hard scatterings. But most of the collisions, most of the events in heavy ion collisions are, well, are electromagnetic scatterings, for example. Or here we see the two most important, are not hard scatterings. And here we see the two most important effects of so-called bound-free pair production and electromagnetic dissociation. So these are processes that, these are the processes that described here. So they lead to the emission of positrons or neutrons. And the problem with these things is twofold. So you can see that these kind of processes, they have a much larger cross-section. So here, if you're in this table, you see this is the total cross-section of lead collisions, and you see hard inelastic scatterings, which is what you look for when you do your physics searches typically, are only a very small fraction of this total number. Most of them come from the bound-free pair production, electromagnetic dissociation. So these two processes shown down here. And why is this problematic? Okay, this is problematic for two reasons. First of all, this leads to this formation of so-called secondary beams. So as you can see in the final state of this processes, you see there are particles with the wrong charge to mass ratio. Charge to mass ratio, not the one of the original lead nuclei that went inside. And this means that they're affected in a different way to magnetic fields. So recall that in the LHC, there are magnetic fields that are supposed to keep the beams in the right place. And of course, these magnetic fields have to be adjusted. Well, whether you collide protons or heavy ions, they're a bit different, but they have to be adjusted in a way that particles with a charge to mass ratio, during proton runs of a proton and during heavy ion runs of a lead nucleus, are being kept on track. Now, if you have particles with a different charge to mass ratio around, they will not follow the same trajectory in these magnetic fields. So they will they become like loose cannons, and they go somewhere random. And this somewhere random can be quite dangerous because they can hit one of the LHC magnets and then they inject energy there, and the superconducting magnets don't really like it if you inject energy there. They heat up, the superconductivity is lost, and then the magnet quenches, and this like shuts down the whole LHC. So this is a huge problem. So these secondary beams composed of particles with a modified charge to mass ratio that were produced in these two types of processes that I just mentioned, these secondary beams are a serious limitation. So we have to keep the luminosity low enough that one can handle these secondary beams. Luckily, the LHC people have found a way to solve this, another way to solve these problems, and they can be dumped. Now they can be dumped into a place where they're not dangerous, where they don't hit a magnet. So the place was found where the magnetic fields can be used to dump them without hitting a superconducting magnet. All right, but the second problem is, so this problem is solved. The second problem that limits the integrated luminosity during heavy ion collisions is the beam lifetime. Because again, recall that most of the collisions here are not the hard collisions that we look for, but all these non-hard collisions up here, these processes, they take ions out of the beam, so they thin out the beam. So here you see how the heavy ion beam decays, so the luminosity decays as a function of time, and you see it decays quite rapidly for heavy ions. So this is time here. Time is literally time in the sense of time of the day, so 9 o'clock, 12 o'clock. And you see the integrated luminosity decreases very quickly with heavy ion runs because these uninteresting collisions take out too many ions from the beams. So this can be estimated quantitatively with a bunch of formulas. So it is common to parameterize the number of ions per bunch in this way. So here it's the number of ions that can be put into one bunch as a function of the mass and the charge of the nuclei. And the way to parameterize it is usually to put it in relation to the number of ions per bunch that can be done with lead collisions. Lead is what has been done so far. And then form the ratio between whatever other nucleus one might want to collide, and then Z is the charge of this other nucleus. And then one simply parameterizes this number, how many ions of a given type one can put into one bunch, in relation to what would be possible with lead, is characterized by this exponent P here of the charge ratios. And now one can, okay, if one now wants to reproduce this curve, so how quickly does the beam thin out? What one can do is one has to solve. It's a very, well, if one wants to do it in full glory, it's a complicated problem for the experts. But if one wants to do it in the back of envelope way, how theorists like I imagine it, then one just has to solve a simple differential equation. And an important factor here is, of course, the beam lifetime. And the beam lifetime is, of course, determined primarily by the total cross-section to which all of these processes, the wanted hard scattering and the unwanted ones contribute, electromagnetic ones contribute. And then one has to see, so then apart from the cross-section, which determines the beam lifetime, there's one other important quantity, which is the so-called turnover time. So because if you refill the beam, it takes a certain time to refill the beam. And then the logic goes as follows. So if you let the beam run for very, very long, then the number of particles in the beam decays very rapidly. And at the end, you're running the accelerator with a very, oh, sorry, that's my son. Sorry, I'm still in home office. Then we are running the collider with a very low instantaneous luminosity. And of course, then the event rate becomes very, very small. So you want to refill the beam because if you have a very low instantaneous luminosity, you're sort of wasting running time of the machine. On the other hand, each time you refill the beam, you lose time in which there is no beam. So you have to calculate what is the optimal time when to refill the beam. And that can be calculated with this formula given here, where TA is this turnover time that is needed to refill the beam. And then one can calculate this optimal sort of, the optimum for which we optimize the time averaged luminosity. So rather than optimizing the peak luminosity, what you want to do is you run the LHC for an extended period, which then you want to optimize the average luminosity. And of course, in all these equations, what enters is this parameter P. So what people are looking into now is how this maximal average luminosity can be optimized by using ions other than lead. So to begin with, people collided lead because it's the heaviest thing you can collide. So you have a big nucleus, it's good for quark, gluon, plasma. But now people are thinking, people in the heavy ion community are thinking that it might be interesting to collide other nuclei than lead, because it might be better for this integrated luminosity. And the reason for that being is that lighter nuclei, of course, for lighter nuclei, because these contributions from these unwanted processes like electromagnetic dissociation or bound-free pair production, these contributions will be smaller. So the ratio between interesting events and not interesting events will be better for lighter nuclei. So in lighter nuclei, of course, you have less nucleons per collision, but on the other hand, you might be able to run the beam for longer because it doesn't deplete so quickly. So therefore, the question, what's the best ion to optimize this integrated luminosity is, or average luminosity, is a non-trivial one, and it strongly depends on this parameter P, which is not really well known for most ions. Okay, but this whole discussion was a theorist's view on, let's say, collider issues. Now, let me come back to the topic that I'm actually talking about, which is BSM, beyond the standard model searches in heavy ion collisions. And of course, what we are interested in, if we want to look for beyond the standard model physics in head-on collisions, is the number of nucleon-to-nucleon collisions. And if you look at this table, okay, we have two copies of the same table that are basically different, correspond to different choices of this parameter P, an optimistic choice and a pessimistic choice. So I recall P is the parameter that governs how many nucleons you can squeeze into one bunch. And for most of these types of nuclei here, it is not really known what this parameter is. So therefore, I'm presenting a pessimistic and an optimistic choice. And then in this table, you see basically what is the luminosity, what is the beam lifetime, what is the initial luminosity, what is the beam lifetime, what is the average luminosity, and how does that translate into sort of the time averaged number of nucleon-nucleon collisions that you get. And then you see, if you look at these numbers, that there's no way that heavy ion collisions ever will be competitive with this. So you see the integrated luminosity is so much lower that even if you take into consideration the fact that each nucleus has a nucleons, so that each time you have a collision, you have an A square enhancement, even if you take that into consideration, which is folded in here, you see that the number of collisions, like the proton is normalized to 1, is just much, much too small to be competitive. However, now comes the thing into play that I said before about the backgrounds being different. So if you could observe all events, then it would be hopeless to search for new physics of this kind in heavy ion collisions. However, not each event can be seen. And let's explore a little bit what can be done by changing the triggers. So by taking advantage of the fact that a larger fraction of the events can be recorded with heavy ion bands. Now, I'm going to exploit this for a specific model, the so-called seesaw model, which is a minimal extension of the standard model by so-called right-handed neutrinos. So this model is given by this Lagrangian here. And basically, if you look at the standard model, here is the particle content of the standard model. One thing that you can notice when you look at this is that all fermions here on the left, you have the fermions. So up here, they're the quarks. Here are the quarks. Down there, they're the leptons. Altogether, these are the fermions. And there are the gauge bosons here. And then there's the Higgs boson. One thing that you can notice in the standard model that all the fermions are known with two types of chirality, so as left-handed and as right-handed, except for the neutrinos, they are only there with left-handed chirality in the standard model. And okay, if you add right-handed neutrino to the standard model, this could potentially explain several problems like the observed neutrino masses. It could lead to so-called leptogenesis, which can generate the matter-antimatter asymmetry of the universe and therefore explain the origin of ordinary matter in the universe. Or there can be connections to dark matter. So this is how the Lagrangian looks like. You add to the standard model this right-handed neutrino. And this right-handed neutrino nu R couples to the standard model Higgs doublet and standard model lepton doublet through a matrix of new cover couplings F. And because it is a Majorana particle, well, it is a gauged singlet, it can be a Majorana particle and it can have a so-called Majorana mass. And this Majorana mass here introduces a new unknown mass scale in nature. Basically, we don't know what the Majorana mass of this particle is. And if you do this addition to the standard model, then after electric symmetry breaking, the so-called seesaw mechanism does two things. It gives a small mass to the ordinary neutrinos. So the ordinary neutrino mass eigenstates, here called nu, are given by a superposition. This is the neutrino mixing matrix, a superposition of the standard model SU2 doublet, left-handed states, but with a small admixture of this right-handed neutrino, where theta is a small mixing angle. And this small quantum mechanical mixing basically gives masses to the ordinary neutrino, and the magnitude of these masses is roughly given by this new Majorana mass scale that was added to the model here, and 2 powers of this mixing angle theta. And since theta is a small number, then these masses should be small. And okay, this can also be expressed in terms of the Higgs-Wef, the U-cover coupling, and these mass scale. And then you see why it's called seesaw mechanism, because if I write it in this way, I can see that if I make this mass scale heavier, then the neutrino masses become lighter. So if this guy is heavier, then the normal neutrino becomes lighter, and this explains why the neutrinos are so light. This is somehow hidden when writing it in this form of m and theta, because what is hidden here is that theta is inversely proportional to the capital M. Okay, but that's not the point here. The point is that if we explain the light neutrino masses in this way, the prediction of the model is that there are additional heavy neutrino states that are almost singlets, so they basically don't interact with the standard model. They only interact with the standard model particle via this small mixture theta. So there are these heavy mass eigenstates. They are basically almost entirely this right-handed singlet state, but they have a small admixture suppressed by this mixing angle theta of the ordinary neutrino, left-handed neutrino, and via this quantum mechanical mixing, they feel a theta suppressed version of the weak interaction. Therefore, bottom line is there's this interesting new particle that has a mass m, and the interactions of which can be characterized by some mixing angle theta, and this new particle can explain important things like neutrino masses, the baryon asymmetry of the universe, so the matter-antimatter asymmetry of the universe, or can be important in the connection of dark matter. So let's look how we can look for such particles at the LHC. So the effective Lagrangian that one has to look at looks like this. So this is how this particle couples to the W bosons and Z bosons in the standard model. And as you can see, this coupling is always suppressed by this mixing angle theta. So the way how to see this kind of particles in the LHC is either in the decay of W bosons directly, so the W decays into a lepton in this particle, and then this particle decays. And this decay, because this N particle can be long-lived, this secondary vertex can be displaced. Or you can alternatively make these guys in the decay of B mesons. And to study how the sensitivity of different experiments to this, we performed a search, we performed the displaced vertex search. And to remove the standard model backgrounds, one can require a minimum displacement of this displaced decay here of 5 millimeters. That can be seen here, because here you see the lifetime of various different standard model particles, in particular mesons, and you can see that if you require a displacement of 5 millimeters, then you are safe that you are kind of outside the mess that is created by the quark gluon plasma, for example. And we also, impose this invariant mask cut of 5 GeV to remove the backgrounds from the interacting with the detector material. All right, so let's look at the first process, this heavy neutrino production in W decays. We see that this is pretty much hopeless in heavy ion collisions. Well, hopeless, not totally hopeless. So here we see the mass of the heavy neutrino, and here its mixing angle. The gray stuff is existing experiments. Here we see what proton collisions can do. Here we see what lead collisions can do. Oops, it's deep inside the region that's already excluded. And here we see what argon collisions can do. And the shading of the area is because for different choices of this P factor that we say is not known, we get this or that. So here we've seen that argon collisions can potentially exploit parameter space that is not excluded by current searches. However, by the time that argon collisions, if the LHC chooses to perform argon collisions, have exploited this, the proton collisions would already have ruled out this range. And for a fair comparison, this is done for equal running time, I should add here. The other thing that is done is that in order to take advantage of the different triggers, we have here imposed a 25 GeV cut on this transverse momentum of the leading lepton in the P collisions, and we have reduced that trigger to 3 GeV for the search in heavy ion collisions. But we see that in spite of this reduced triggers, the heavy ion collisions aren't that competitive. Well, the reason for that is that in this process, most of the muons have large transverse momentum anyway, so reducing the trigger doesn't help much. All right. While doing these simulations, we realized and confirmed that all of this these simulations can actually be fitted very well with a simple analytic formula in which we can calculate the number of observed events as a function of the luminosity, the neutrino production cross section, U squared, where U squared is now the absolute value squared of theta, so the mixing angle, and then this exponential, which depends on the extensions of the detector, so the minimum displacement and the maximum size of the detector, L0 and L1, and the mean free path of this heavy neutrino before it decays. In this simple analytic formula, you can see here it is compared to the simulation. You can see in this color heat maps that it gives a rather good approximation. So one can use this analytic formula. Now we want to study the production in B decays, and we can then use this simple analytic formula to estimate the number of observable events. And one thing that is important here is because the formula depends not only on the extensions of the detector L0 and L1, how minimal and maximal displacement that can be seen in the detector, it also depends on how far this heavy neutrino flies. And how far this heavy neutrino flies before it decays depends not only on its lifetime, so the lifetime in its own rest frame is determined by by such relation here. So it goes as a square. The decay rate goes as a square of this mixing angle in the 5th power of its mass. But in order to determine how far it gets, you also need to include the boost. And to include the boost, you need to know at which momentum this particle is produced. So for that, you need to look at the differential cross-section for B mesons. If you want to look at the production of these particles in the decay of B mesons. Here, there's theoretical simulations. It can be some good agreement with the experiment. And this can now be used as to estimate, to calculate the momentum distribution of these heavy neutrinos. And well, this momentum distribution of the heavy neutrinos can be compared to two processes. It can be calculated in a simple way. If one looks at two different extreme cases, one can on one hand look at the momentum distribution of the beam meson itself, or one can look at the process that can be observed, where the beam meson decays into a standard model neutrino. So these processes are known, and for this there's data. And of course, if we have, instead of decaying where the beam meson decays into a standard model neutrino, a muon, and something else, if we have a heavy neutrino here, the kinematics will be different, because if you give a mass to the standard model, if you give a mass to the neutrino, it gets less momentum than in the case as if the neutrino is massless. Okay, in the one case, we look directly at the kinematics of the beam meson itself. In the other case, we look at the kinematics of where the beam meson goes into a massless neutrino. And so the momentum of the heavy neutrino has to be somewhere in between these extreme cases. And to illustrate how much changing the trigger is, that we look here. So this is the PT, not the total momentum. We see what is the trigger in standard PP collisions, and what is the trigger threshold that we can use in heavy ion collisions. So these 3 GeV is basically determined by the size of the magnetic field of CMS. The particles still need to get out of the magnetic field in CMS. And if you see at this differential cross sections, at this production, which give you the production rate, you see that it really makes a huge difference in the production in beam mesons. If you cut here, if you only consider events up above this line on this side, or if you consider events above this line. So most of the distribution is actually below this. And if you do this, you realize that indeed, if you look for the heavy neutrinos in B decays, oh, sorry, there's a mistake here. This should be a B decay. This should be a B decay. This is the wrong picture. This should be a B decay. I'm sorry about that. Then it turns out that in this case, because losing the trigger really gives you access to most of the events, you can see that if you do the same plot, here's the mass and here's the mixing angle, you can see that here the proton sensitivity can be estimated to be this. The proton sensitivity can be estimated to be this, the blue line. The lead sensitivity would be lower, but if the LHC is run with lighter ions, which is what is being considered to minimize the losses, what I discussed before, then the argon runs could be more efficient than proton runs. And quite interestingly, the parameter space that is being probed here corresponds to the parameter region where these heavy neutrinos could simultaneously explain the masses of the normal neutrinos and the matter-antimatter asymmetry in the universe, so the origin of matter in the universe. Again, this shaded region, hashed region, corresponds to the uncertainty in this p factor. So this is if you place these these heavy neutrino searches in heavy ion collisions in the bigger picture of heavy neutrino searches. So this is the mass of the heavy neutrino. This is its mixing angle. The gray region is excluded by existing experiments, well, past experiments, and all these different colorful lines tell you the sensitivity of proposed future experiments or proposed future searches. And you see there is a corner in the parameter space that could be exploited with heavy ion collisions. So this follows pretty much the philosophy that heavy ion collisions probably cannot replace proton collisions in the search for new physics, but they can help to exploit corners in parameter space that are difficult to access with the standard searches. And that brings me to my summary. So I've discussed, so heavy ion collisions can be used to probe new physics. And there are some scenarios in which parameter regions are accessible to searches in heavy ion collisions, where those are more sensitive than proton collisions. So examples that I've given are magnetic monopoles, the Axion-like particles, and a certain part of the parameter space for this heavy neutrinos. But there are other examples which are summarized in this paper, in this report paper that we published that I mentioned before. And this can help to fully exploit the discovery potential of the existing facilities and to turn every stone before we build a new collider. So I believe this is a very interesting and hot topic in which there's really a lot of room for new ideas and new proposals. So there's room for seminal ideas. And because of this, we're going to organize a second workshop, originally meant to be organized at ECT Star, but of course, because of this pandemic situation, this will not be possible. So it will be remotely, but we nevertheless hope for very active discussions. One of these topics of these workshops will be to outline a contribution to the snow mass process. So there's already a letter of interest in the snow mass process for this, and we're going to there is no mass paper on this, and well, apart from bringing together community and collecting new ideas, another purpose of this workshop is to move forward with this process. And the income, as I said, this is a young topic, and the input of anybody to this is very welcome. Thank you very much for your attention.